Now it has come. Yes, a very good morning to all of you. Am I audible and visible to everyone over there? Yes? Okay. So I think there was some technical glitch which was there. So thank you for being patient over there. Okay. So without any further delay, we'll start off with the lecture. And I think what was the last thing which we have studied in the last lecture, if I'm not wrong? VACPR table, right? Yeah. Fine. So we'll start off with the another method. And again, the same way we have done, I'll take up your doubts later on, right? Just pay attention and kind of, focus here, whatever is going on. Okay. So let us go for n/2 method for predicting geometry and shape of the species using VACPR theory. So when I'm talking about geometry here, I'm talking about the electron pair geometry. Okay. This is a kind of shortcut by which you can find out what is the kind of electron pair geometry and what is the shape of that particular molecule, right? So at present, you all can write down the formula along with me and we'll definitely be able to understand using some examples, right? So here, just take this n as any number, okay? What is this n/2? So basically, we are going to write down half of, so n/2 means half of n, right? And now we are going to write down for n what it is representing. So it is representing number of valence electrons in central atom plus the number of monovalent surrounding atom plus or minus charge, right? So this is what is your n/2, okay? Now here I'm writing where VE is representing valence electrons. You are having Ca, which is representing central atom, and you are having Sa, which is representing the surrounding atom. Okay. Now the thing is here, what is this n/2? When you put all these values from a given species, what is this n/2 going to tell you? N/2 is going to tell you about how many number of surrounding atoms are there and how many number of lone pair of electrons are there on the central atom, right? So here this is going to tell you the number of other atoms. When I talk about other atoms, we mean the surrounding atoms plus the number of lone pair of electrons on the central atom. This is what is the information which is going to get conveyed from this particular n/2 value, and that is what we are going to see. Now here few things to take care, that we have written plus or minus charge. So already we know that in chemistry, if at all we are having any cation, we always reduce the charge. And that means suppose something x plus 2 is there. So we always write down minus 2. And that means we are decreasing that and subtracting the charge. So we are writing that only if the species is cationic, then subtract the charge, right? And if the species is anionic, then add the charge. Okay. And once we get the n/2 value, doing all those things there, that means adding the valence electrons, adding the surrounding atoms which are monovalent in nature, then what you need to do is compare n/2 value with the VACPR table to predict the shape and electron pair geometry. Right. So do one thing, you first copy down this, all of these points, and then definitely quickly we are going to understand this, and it is not a very difficult one. It's kind of a simple thing, and this will be really helpful for you. Once you just write it down, let me know so that we can proceed further. Yes, are we done writing there? Okay. Now let us see the utility of this particular thing. Suppose, for example, if I give you NH3, right? Now, for calculating n by 2, what you'll be writing half. Don't write 2 times this 1 by 2. I am already writing 1 by 2 for that n by 2. Now, how many number of valence electrons here? For nitrogen, that is the central atom. And see, in this formula, when we are writing, we are neglecting the divalent atom here, which is basically your oxygen or else any other like trivalent, okay, surrounding atom, which will be making more than one bond with the central atom, right? So as of now, if at all oxygen is there, which is anyhow divalent, we have seen when we are drawing the structures. So basically it makes double bond usually, right? Neutral oxygen atom. So basically now at that, like for this moment, you can leave that particular oxygen in this n by 2, right? We'll see that kind of example. Now the thing is, how many valence electrons here in nitrogen? That is a central atom. It is 5. Surrounding atom is hydrogen. That is monovalent because it always forms a single bond, right? So you are going to have plus 3 here. So what is the value you got? You got 4. Now you take it like this. You have to arrange 4 things around the central atom, right? So when you have 4 things to be arranged around the central atom, the electron pair geometry is tetrahedral, right? 4 things. But out of those 4 things, we are having 3 things as atoms. So definitely one will be your lone pair. Getting it? So what is the class of molecule we got? We got this as AX3E. Okay. So the thing is electron pair geometry. Electron pair geometry here becomes tetrahedral, and the shape here becomes, shape of that species becomes trigonal pyramidal, right? Now let us go for the second one. Suppose if I give you CO3 minus 2, let us say like that. Okay. Now here, if at all I am writing n by 2 value, see, first of all, we have to write down central atom is carbon. We got to know that, okay, 4 electrons are there in its valence shell. Now the thing is, surrounding atom is not monovalent, right? It is basically bivalent. So we have to not include here in the formula, right? But we have to include the charge. Minus 2 means gain of 2 electrons or extra 2 electrons. So basically, are you getting 3? Now the thing is, this 3 number, it is telling you how many things to be arranged around the central atom, and there are 3, right? Now you bring back the existence of oxygen. How many oxygens are there? There are 3. Now you cannot neglect oxygen. Getting it? Only while calculating the n by 2 value, you are not including it. But once you get the number, you please call back your oxygen in your memory, right? So you are having 3 there, 3 things to be arranged around the central atom, right? So 3 things means all the 3 are atoms only now. So basically, there are no lone pairs here. So you are having AX3 class of molecule. And for AX3, do we know that the electron pair geometry is trigonal planar, and the shape is also going to be same because there is no lone pair. Getting it? So please note it down, and after that I'm going to give you few, right, so that you can do it and we can discuss that here. Is there any issue here to anyone understanding these 2 problems? You have to go on the similar line only. It's fine, right? There is no issues. Okay, good. Have we written it down? Okay. Then I am going to give you a few problems. Give it a try. Okay, all of you. And make sure when you are doing this problem, you are not flipping your pages back for referring to the VSCPR table, because I asked you to remember it logically, right? Hopefully you people have done that. So let us go for yes, I'm giving you these problems. Give it a try. I'm giving you 5 to 7 minutes of time. I think you will be fine calculating them. Please do it. Okay, is that okay with all of you? Just give it a try and then we'll definitely discuss all of this. Are we done doing up to 6? Only half of the problems I'm asking. Are we done doing up to 6? Okay. Now see here, when I have to calculate this n by 2, that is basically how much? 1 by 2. What is the number of valence electrons? 5. 4 is the surrounding, minus 1. So you are having basically 4. Now the thing is, 4 things to be arranged and you are also having 4 here. That means 4, all of them, they are atoms. So basically you are having AX4. So my electron pair geometry is also tetrahedral. And the shape is also basically tetrahedral. Are you getting it? This EPG is electron pair geometry, okay? Because it's entire thing, it's taking a little bit more time. That's the thing we have gone for this particular shortcut. This is not a kind of universal shortcut, okay? Now, again here, n by 2 you calculate. This time half of, you will be writing 6 for the number of valence electrons. This time, will you be including oxygen here? Will you be including oxygen in case of sulfate? No. Good. So the thing is, here you are going to have this as 4. So 4 things to be arranged and you are having 4 atoms. So that means it is the same, right? Electron pair geometry. This is AX4 type. So that is tetrahedral. And in fact, you are having shape also as tetrahedral. Got it? Good. Now, for this, what is the n by 2 value? N by 2 value is half of, you are having 6 valence electrons. For this, you are having 5, right? Now the thing is, you have 5 things to be arranged around the central atom, but how many atoms are there out of that? 4. That means 1 will be lone pair. So you are having basically AX4E type. So electron pair geometry becomes what? Trigonal bipyramidal. And the shape here is going to be seesaw. What is the other name for seesaw which we have seen? Other name for seesaw? Folded square is one. Then there is something which starts off with D. Distorted. Something like distorted. Yes, good. So distorted tetrahedral. Okay. Now when it comes to XeF4. So for XeF4, n by 2 is basically 1 by 2, 8 plus 4. You are having 6. Right? So there are 6 things to be arranged. Out of that, 4 are atoms. So definitely 2 will be lone pair. So you are having AX4 E2 type. So what is the electron pair geometry? That is basically octahedral. And what is the shape of this? This is going to be square planar. Right? Remember that? Square planar. Hopefully you people did this correctly up to this 6th problem. Now let us go for this particular 7th. So in this case, what we are having is XeF4. So if at all I want to go for N by 2, let me just use this another color. So here if at all I am writing N by 2, it is half of, this is 8, so 4. So again it is AX4 type. So electron pair geometry is tetrahedral. And in fact shape is also going to be like that, okay? Shape is also tetrahedral only. Now XeO3F2, N by 2 what you are having is half of 8. 3 we cannot have, so you are having 5. So there are 5 things to be arranged and 5 things are atoms here. So basically you are having AX5 type, good. And people are able to say TBP geometry, right? So this is electron pair geometry. That means EPG is also this. And you are having basically the shape also like that. Okay. Now when it comes to I3+, just treat it like I is the central atom, 2 iodines are the surrounding atom, right? So if at all you are calculating N by 2, so basically it will be half of 7 number of valence electrons here, 2 surrounding iodine and 1 charge is there, right? So you are having again 4 here. Now out of this 4, around the central atom there are 2 atoms which you already know. So 2 will be the lone pair of electrons. So you are having here AX2E2 type. So electron pair geometry being tetrahedral. And you are having basically the shape here which is going to be bent or angular, right? Hopefully everybody got this. I3 plus and I3 minus is the place where students generally tend to get confused. I hope this you people have got it, right? Is there any issue with the I3 plus? And the last example in this category I have given you I3 minus, right? Now the thing is here N by 2 if at all I have to calculate it is half of. Again the same way you treat it, iodine surrounded by 2 of the iodine atoms and minus 1 is on the iodine. So you're having 7 plus 2 plus 1. So you're getting 5. So now around the central atom total 5 things to be arranged. Out of that 2 are atoms. So basically you are having AX2 E3 type. So electron pair geometry becomes TBP and the shape will be becoming what? It will be basically linear. Remember when we are having 3 lone pairs. Yes, are we clear about this? Is there any doubt here? Right, so we are done with this particular N by 2 method for calculating this VSEPR. So if at all you know what is N by 2 and you know VSEPR table, then you are fine. You can easily sail through this. Now, let us put the heading for the next topic, which is hybridization. And one more small question I'll ask you. In this case, you tell me, if at all I am giving you ClF3, suppose, this is related to VSEPR only. In this case, if at all I ask you the angle, suppose, or else let me give you SF4, that will be better. Like this, we will be writing SF4, right? Now, if at all I ask you what is the angle here for equatorial and then again axial equatorial or between axial axial, what is the angle you are going to tell me? See, that's what I expected, and the answer is coming like that. Whatever is, ideal geometry, if at all you are forgetting people, like this, I might have told you, everything here. So if at all the bond pairs are there, then to find axial equatorial 90 degree, equatorial equatorial 120 degree, axial axial, it will be 180 degree. But what about this thing? For some, like think little bit. If at all this lone pair is there, it is going to repel it, right? You will be having something like this. Because of the repulsion. So will this bond angle between axial will remain 180 degree or it will become lesser than that? And even it will not be 120 degree between the equatorial. Are you getting it? So there is a role to play for this particular lone pair. This is not for decoration. Are we getting it? So whatever are the, basically whatever is we have put, kind of the bond angles. That is for ideal case. Ideal case means regular geometry. Regular geometry in the sense you are having central atom and you are having all of them atoms are there. There is no lone pair there. Getting it? So be very clear in your mind, because the examiner, if they want to play with you, they can ask you about this. Are we getting it? And the person who used their sir, Anna, please do not change my gender. Anna, I am ma'am, so better write down ma'am. Getting it? Yeah, better. Okay. Are we done here? Okay. Now come back. So I hope that particular thing is like clear to you, how to identify VACPR and all those stuff. Okay. Now the thing is, when it comes to hybridization, let us go for who has given it. Pauling and Slater, right? Now the thing is, this hybridization, what is it basically, or else why it was thought of, right? So we'll see all those points, but at present you just understand that basically we are having, some kind of intermixing of atomic orbitals which goes on here. That's what is hybridization. Hybrid, that means you might have heard of the term hybrid cars, no, right? Or else at your home also, hybrid thing, khichdi, if at all your mom is making, it is hybrid only of dal and rice, right? So basically hybrid means you are combining two or more things there, right? Now the thing is, here, if at all I go for the definition of it, so it means the intermixing of atomic orbitals of slightly different energies to form new orbitals of equivalent shape and energy. You first write this down, then I'm going to explain you why we basically need to, or else why the people thought that this particular concept has to be brought into picture. Okay, we'll understand that, but definitely when I am explaining that particular thing through a particular example, I don't want you people to write it, because there is a sequence in which you have to write, but I need to explain that first so that this concept gets clear why we have to read this. Are we clear on that particular thing? Right? So just wait. You have to write that, but in a particular sequence when I tell you. Okay? Are we done writing this particular definition? Let me know. Okay. Now, let us try to understand this. So whatever I am going to write now, please do not write it. You first understand it. Okay? Formation of methane, right? When I write down this ground state electronic configuration of it, I am having 1s2, 2s2, 2p2, right? So if at all I look for carbons, like electronic configuration, I'm just having two unpaired electron here, right? Now the thing is, how many bonds this carbon is making in CH4? How many bonds? It's making 4. So we are first going to understand according to VBT, and then we'll see what was the problem with the VBT so that this concept has been brought up, right? So the thing is, if at all it is like only two unpaired electrons, so ideally it should make two bonds only, because according to VBT, the atomic orbitals, valence shell atomic orbitals containing these electrons, they'll be overlapping with the atomic orbital of the other atom to basically form a covalent bond. So basically I should have 4 electrons here. So what we are going to do is, for excited state, can I write 1s2, 2s1, 2p3? So you are having here 2s1 and 2p here. So basically you are having 4 unpaired electrons, right? Now the thing is, if at all we go by VBT itself, so the thing is you are having, let us say this is 2px, this is 2py, and this is 2pz, right? Now the thing is, if at all for carbon, if I show that this is x direction, and let us say this is 2px, and there is one electron here. Now the thing is, hydrogen's 1s, it can come from this x axis, or else x as the internuclear axis, right? Yes, Sindhu? Please kind of, wait for it, Do not write in between when something is going on. The chat box is not provided for, sharing whatever you want there. Only when I am like explaining something, you are having certain doubt, please ask that. That is my humble request, Beta. Because that basically breaks the entire flow of the lecturer. Please don't write there. So here you are having sigma bond, right? Now the thing is, this sigma bond, in which direction it is lying? It will be lying in the x direction, right? Now the thing is, similarly, if at all I am having 2py, let us say, है ना? So one electron here, this is y axis. So again you are having hydrogens 1s, right? It can come from basically x direction and x direction saying. It can come from basically y direction, overlap from that, and it will be forming a sigma bond, and this will be lying in y direction. Similarly, if at all it is z direction, right? So you are having something like this, one electron here. Let us say this is z direction. You are having one electron, then hydrogen 1s. It is having one electron. It can come from z axis, or else z as the internuclear axis. You will be having a sigma bond here, and this will be lying in z direction. Yes. So what we got? We basically got 3 of the sigma bonds which should be mutually perpendicular to each other, right? 3 CH bonds. Okay. Now the fourth one, if at all we talk about, so the fourth one is carbon's 2s is there, right? This is 2s of carbon, and you are having hydrogen's 1s, right? So this sigma bond will be formed, but can we predict what will be the direction here? Can we say with too much of certainty that it can be formed in x direction, y direction, z direction? Because we know that s orbital is spherically symmetrical, right? So the thing is, according to VBT, basically what we are having is, for the CH4, we are having 3 bonds which are perpendicular to each other. And the one bond, we cannot be very specific which direction it is, right? But ideally when it was seen, or else in reality it was seen, so basically you had CH4 like this. All the bond length same, all the bond angle also same. 109 degree, 28 minutes, or else 109.5 degree. So then people thought, if at all methane exists like this, that means all the bond length same, all the bond angle also equal. So then they thought that basically somewhere this particular molecule, definitely the atomic orbitals which were starting, like from the beginning, whatever are the atomic orbitals, they are equivalent in their energy and shape. Then only it is possible to have this, right? Then they thought of intermixing. So let us say energy here. For carbon, I can show this is 2s, this is 2p. Let us say this is 2px, 2py, 2pz. You are having 1 electron. Just now we have seen in excited state. Now the thing is, when it is undergoing hybridization, so what will happen? 1 2s and 3 2p orbitals are participating. So basically we'll be getting 4 hybrid orbitals, and they'll be named as sp3. This name will be coming on the basis of how many orbitals are participating there, and you are having 1 electron. Now if you carefully observe, the energy level is kind of intermediate, because these atomic orbitals, they have intermixed and they have redistributed their energies to give the hybrid orbitals of equivalent energy and shape, right? Now the thing is, if at all I am having this particular kind of hybrid orbital, it will be looking somewhat like this, plus minus and the nucleus here. From where it is coming, you are having S like this, you are having P like this, right? Remember, and basically these orbital sign which you see, basically they are the wave function sign. So when you combine them, something like this. So plus constructive interference, a bigger lobe. Plus minus destructive, right? So you are having a smaller lobe. So ultimately each hybrid orbital is going to look like this only, right? So how many hybrid orbitals I am having now? 4 hybrid orbitals. So 4 things, or 4 hybrid orbitals, they arrange themselves in a stable fashion in a tetrahedral manner like this. You are able to see this? Okay. Now, this is what is like sp3 hybrid orbitals of the carbon, how they have arranged themselves. Now hydrogen can come with its 1s, having 1 electron there, overlap and form this, right? So now you got the sigma bond, and from this, whatever the CH4 we are getting, no, that is having here 109 degree 28 minutes or else 109.5 degree. So here we will be able to say all the bond angles and bond lengths are same. Getting it? So the thing is, for hybridization, be very sure that it's basically the central atoms. For the same atom, we are intermixing the atomic orbital. And again, don't think that, just putting all these atomic orbitals somewhere in a container and you're mixing it. It doesn't happen that way. Basically, it's a mathematical model, right? There is a certain kind of complex mathematics which goes behind it. But the good thing is we just have to take conclusion from this particular mathematical model which is there. Getting it? So ultimately, this hybridization again is a hypothetical concept because it has been brought to understand the shape of the molecules which other theories were not able to explain. Are we clear on that particular thing? Right? Now what we are going to do is, you will note it down later on, but at present let us write down some features here or some important points. Okay? So you can write along with me. Hopefully it is understood like why this particular thing has been brought into picture, hybridization. Are we clear on this? Okay. So now let us write down salient features of hybridization. Now the thing is, why we are writing this thing is, basically we want to have, like, if at all some theoretical question is being asked. Okay. So the thing is, at that time, maybe they can give you 3 to 4 postulates and they can ask you which of the following is incorrect, correct. So for that reason only we are writing this. Okay. So make sure that you are writing along with me. So the first one is, only those atomic orbitals having atomic orbitals having comparable energies take part in hybridization. So we cannot have any random atomic orbitals mixing, right? It has to be like, they have to be very, like, slightly different in their energies, otherwise it's not a useful exercise. Second one, it is a hypothetical concept. Just now I told you that basically it is mathematical model, right? It is a hypothetical concept. Next, the hybrid orbitals, the shape of hybrid orbital is given by, so 2 lobes will be there. This is the bigger lobe, and this bigger lobe is used for bonding, and this is the smaller lobe. This is not used for bonding, okay? Only the bigger lobe which is there. Better overlapping possible there. Now, the hybrid orbitals take part in sigma bond formation and pure p orbitals take part in pi bond formation, right? That means pure p, when I'm referring to, it is basically those p orbitals which did not participate in hybridization. That's what is the meaning of pure p, okay? Then the number of hybrid orbitals formed is equal to number of atomic orbitals taking part in hybridization. Right? So for example, if at all I say there is one s orbital and one p orbital which is participating in this hybridization. They are undergoing hybridization. So at that time, basically, 1s and 1p is combining. So I'll be getting sp hybrid orbital. But the thing is, how many sp hybrid orbitals? I'll be having 2 because 1s and 1p. So the number of hybrid orbital is going to be equal to the number of atomic orbitals which participated in hybridization. So if at all I'm having now 1s and 2p orbital, again for hybridization you are going to have sp2 hybrid orbitals, and how many in number? 3. Getting it? Then empty, half filled and fully filled atomic orbitals can take part in hybridization. Can take part in hybridization, right? So it's not necessary that only half-filled atomic orbitals will be hybridizing or else undergoing hybridization. It could be half-filled, it could be fully filled, it could be empty also, right? Okay, now another postulate here. As the percentage S character increases in hybrid orbital, it becomes bulkier and shorter, and as percentage P or percentage D character increases, it becomes longer and thinner, right? Yes, definitely, Matt, I'll do that. And some spammers will always be there here. Yeah, I have done that. Don't worry about it. Let them be at peace. Some anti-social people always exist in this world. Yes, I hope you people have written it, right? Okay. Okay, so these are the salient features of this. Now the thing is, let us make one particular table, everyone. And this table is going to be important because directly some question could be there. Okay. Now here, let us write down basically hybridization. And in fact, if somebody missed out on writing these salient features, need not worry. In your NCERT, they've already given this. Okay. So hybridization, then type of atomic orbitals involved, and then you are having the geometry associated with it. Now the thing is here, first one is, in fact, let us say geometry or shape associated with this. Now first one is sp hybridization. In case of sp, you know that it is going to be 1s and any p orbital, right? So 1s, or else I can just write down ns plus npx or npy or npz. That means at a time I'll be taking either ns plus npx or else ns plus npy or else ns plus npz, right? And this is going to be linear, right? So this table we are just making so that you know that which orbital are being involved in the hybridization over here. Okay. So next is sp2. So here you are having ns, plus npx plus npy, or else you can have npy plus npz, or else you can have npx plus npz, right? Okay, now the thing is, this is going to be trigonal planar, that we have already seen, right? In VACPR, anyhow, in detail we have seen. Okay, now next is, you are having third one, which is sp3. So here there is no doubt, because what is this n representing here? Make sure that you know that n is representing the principal quantum number over here. Okay, so now what you are having is ns plus npx plus npy plus npz, right? And this, what is the geometry here associated? That is going to be tetrahedral. Now the thing is, if at all you carefully observe, we are going for, kind of the steric number here. For sp you are having 2. You are just adding up the powers over there which are present on s and p. Similarly for sp2 also, 1 plus 2, you are writing 3 over there. sp3, 1 plus 3, 4, steric number like that. So here dsp2, for dsp2, basically what I am having is square planar. Now the thing is, when I am writing d before, so d before means I am taking n minus 1d. Suppose it is 4s 4p, then I am referring to 3d over here. That's what is the value of n minus 1. So basically here it is n minus 1. So for square planar, right, square planar will be like 4 in a plane now. So for that we are like, which orbital, d orbital we have to take? We are taking here dx square y square, because its slope will be pointing out in that particular direction. So dx square y square plus ns plus npx plus npy, right? Now the thing is, here you are having basically x and y only, because I have to form in xy plane. Getting it? Square planar. So they can ask you, which d orbital participates in dsp2 hybridization? Getting it? Now, next is sp3d, and we know that it is trigonal bipyramidal geometry, right? 3 in a plane and 1 above, 1 below, right? So can you guess what are the orbitals here? ns plus npx plus npy plus npz plus, you are having for d, you can take ndz square. So you can think of like this, that 3 in a plane, trigonal plane. So xy plane, you think of these 3, right? And then 1 above and 1 below, that will be for npz and dz square, right? Now the thing is, if at all I write down dsp3, only difference will be, we are going to just have n minus 1, nothing else, the same z square here. ns plus npx plus npy plus npz, right? And again it is going to be tbp only. There is no change in its geometry. Only thing is, whichever orbital we are taking, we are writing it like that. Okay, n minus 1. Now there is a very rare geometry which is also associated with this sp3d. This is a rare geometry which is basically square pyramidal, right? And square pyramidal means what? 4 in a plane, 1 above, like that, na? Then only it is like a square base, 1 above, like that pyramid will be there. So now in this case, you are having ns, npx, npy, npz, and you are having n dx square y square. So can you tell me which are the orbitals which will be making the square plane? These are the 4. And then you are having npz, right? This is a geometry which is rare here, but still they can ask you, like, which d orbital is involved in the square pyramidal geometry of this sp3d, right? So that has to be dx square y square. Now next is, you are having sp3d2, which is basically octahedral. Now in case of octahedral, you are having 4 in a plane, 1 above, 1 below, right? So this time ns plus npx plus npy plus npz plus you are having n dx square y square plus you are having n dz square. So are you able to see these 4? They'll be forming the square planar base, and 1 above and 1 below, that will be pz and dz square, you can think of, right? And if at all I write down d2sp3, only difference will be, now in place of n, you will be writing n minus 1. You will be writing here n minus 1 dx square y square plus n minus 1 dz square NS plus NPX plus NPY plus you are having NPZ. Again, it is also going to be octahedral. You can relate to these two terms. You might have heard of that outer orbital complex, inner orbital complex, right? In case of coordination compound, somewhere you might have read it, or else you might have heard about it. Okay, so it is coming from here. Now, the last one is here, sp3d3. In case of sp3d3, what you are having is pentagonal pyramidal, bipyramidal basically, sp3d3. That is PBP, which is pentagonal bipyramidal. I'm not writing it entirely because we have already written that. So 5 in a plane, 1 above, 1 below, like that. So 5 in a plane here, NS, NPX, NPY, NPZ. And then you are having N dx square y square plus N dxy plus N dz square. Right? Now the thing is 5 in a plane, 5 in this plane. Are you able to get that? XY plane itself. And you are having 2, 1 above and 1 below. Right? So that's what is the utility of this particular table. They can ask you which d orbital is involved in the like in this sp3d3 hybridization. Getting it? Please write this and then we'll proceed further. Okay, good. People are raising hands. Is it the doubt you are having? Yes, Sindhu. What is the doubt you are having? Is it the doubt you are having or else you are fine with that? Understood? Okay, you understood. Fine. Okay. I'm asking about Sindhu. Sindhu and some Oppo 883 is there. Like D2 specific. No, you cannot have like that. Ashfaq, you cannot have like that. Okay? Now, hopefully everybody has written this. Now, I want you to write down. Can you write it later on, the formation of CH4, which I have written here? It's available to you, basically. Formation of CH4. Can you write this later on? If yes, then you can just do the thumbs up over there. Yeah, because anyhow I have explained you. So after this, you can just write down the formation of the CH4. And if you want, you can omit these diagrams. Okay. Only thing which is important is I'll just tick mark over there. You have to write down this double tick mark which I am doing. And you have to write down this particular thing. Okay. And then this intermediate part, okay, fine, you can remove it. And then you can write down this, okay, this is important. So can we do that fact? Okay. Now let us try to understand formation of C2H4. So for C2H4, we will first draw its diagram, which we know it is alkene. What is the hybridization here for both the carbon? sp2. And how many bonds one carbon is making? Total bonds made by one carbon. It is 4, na? 3 sigma bond and 1 pi bond, right? So in this case, for carbon, let us write down for ground state. We'll be writing this as 1s2, 2s2, 2p2. Now the thing is, it is making total 4 bonds. So we need to have excited state where we can write 1s2, 2s1, 2p3. So 2s1 here and 2p3 here, right? So 4 unpaired electrons here. Now this time what we are going to do is, on the energy diagram, suppose for carbon I showed 2s, then you are having 2px, 2py, 2pz, one electron here. Now they are undergoing hybridization. So this time we know it is sp2 hybridized. So sp2 hybridized means 1s and 2p orbitals would have participated. So how many atomic orbitals or else hybrid orbitals I am going to get? 3 sp2 hybrid orbital, and one which didn't participate, its energy is not going to change, right? So this is what is pure p orbital, which didn't participate in hybridization. Are we getting it? Now the thing is, you are having sp2 hybrid orbital, okay? Now the shape of this sp2 hybrid orbital is also going to be like this only. Only thing is, if more percentage p character, then it will be like slightly leaner, thinner, right? Otherwise it is going to be like this, huh? Now the thing is, if at all I am having 3 orbitals, so in sp2 you are having basically how many orbitals there? 3 now. So basically what you are going to have is, for one carbon, these 3 atomic orbitals, they are going to arrange themselves in a trigonal planar fashion, right? I'll just draw it. Trigonal planar fashion like this. Plus, 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 sign of the wave function. You are having one electron. For one carbon I have drawn. Right? Now, if at all you carefully observe the sigma skeleton of this structure, one carbon is sigma bonded to another carbon. So that means what? Another carbon's sp2 hybridized orbitals will be like this. It will also have one electron, so it has overlapped here. We're having one electron here. So hydrogen's 1s like this. Here also hydrogen's 1s. You are having one electron here. It can come and overlap like this. Hydrogen's 1s. So the sigma bond story is over. All the sigma skeleton which is there, that's what is sigma bond. This is for another carbon which we are talking about. Now the thing is, this is in xy plane. Now you are having basically pi bond. Hai na? So pi bond will be like 2pz we are talking about. It is going to be perpendicular to it. Right? So that's the reason I'm slightly showing it tilted. Plus minus. It is 2pz, 2pz. One electron there or not. This pure p orbital I'm talking about. So they are going to overlap to form pi bond. So did you understand the meaning of that particular thing? Which I've told you that hybrid orbitals participate in sigma bond formation, right? You are able to see they are undergoing sigma bond formation, and you are having basically what? Pi bond being formed by pure p orbital. You are able to see that? Okay. So hopefully we have understood. Now in case of suppose NH3 is there, you know, I'm just explaining one more point here. That means the fully filled atomic orbitals can also participate in hybridization. So you should understand one thing, that it's not necessary every time that you need to excite the electron before, going for hybridization, right? That's not a prior condition. Here in case of carbon was making 4 bond. In the valence shell of carbon, there were only 2 unpaired electrons, right? So we had to excite it, or else we had to go for the promotion of that electron so that 4 unpaired electrons could be there. Getting it? But now in this case of ammonia, nitrogen is there. Nitrogen is 7, right? We'll be writing 1s2, 2s2, 2p3. We are already having what? 3 unpaired electron here, and nitrogen is making 3 bonds. So we need not excite the electron here. Getting it? Because for excitation also energy is required, right? So what we are going to do is, for energy here, let us say for nitrogen, you are having 2s. And hopefully people are knowing why I am showing it like this, 2px, 2py, 2pz. This is multi-electron system. So based on n plus L rule, definitely energy of 2s is going to be lesser than this 2p, right? So when they are undergoing hybridization, I am going to basically write this as, all of them, they are undergoing hybridization. This is fully filled, right? But still it is undergoing hybridization. You will be getting 4 sp3 hybridized orbitals. And in one of them it is 1 pair of electron, in another you are having 1 electron, right? So now sp3 hybrid orbitals, how are they going to arrange themselves in a tetrahedral fashion? So you are going to have something like this. I can make the smaller lobes later on, right? So you are having plus, 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 minus, minus. Anyhow, these smaller lobes, sometimes for simplicity's sake, they can be removed also. So you're having 2 electrons here, 1 electron here, 1 electron here, right? Now the thing is, this is for nitrogen we have drawn. Now for hydrogen 1s, 1 electron can come. And here there will not be any overlapping here, by the way. Lone pair is lying. Already 2 electrons are there. Okay. And then here you are going to have hydrogens 1s, and here also you are going to have hydrogens 1s. Now the thing is, this is what a sigma bond is going to be formed here. So you are having a molecule like this. We say it is sp3 hybridized. Getting it? Is this clear? Now in case of BeCl2, also think of like that. Beryllium is 4. You'll be writing this as 1s2, 2s2, but there are no unpaired electron. So what we need to do, this is the ground state. So for the excited state, what you are going to write down? 1s2, 2s1, 2p1, so that you are having 2 unpaired electrons. Sorry, only 2 unpaired. We have sent one of the electron here, right? Now the thing is, you know that structure here, BeCl. Are you able to see this is sp hybridized and this is making only 2 bonds, right? So basically again on the energy level diagram, if at all I want to show, for beryllium, right? You are having 2s, you are having something like 2px, 2py, 2pz, here 1 electron, here 1 electron. So they are undergoing hybridization. So for that, you will be getting 2 sp hybridized orbital, each having 1 electron. Now when you are having 2 hybrid orbitals, sp hybridized, so they are going to arrange themselves in this 180-degree fashion. You are able to see this plus minus. For beryllium we have drawn, okay, 1 electron there. Now the thing is, these are the 2 hybrid orbitals which are 180-degree apart from each other. And then for chlorine it is 17 now. So you are having neon and you will be writing 3s2, 3p5. So there is only 1 unpaired electron here. 1, 2, 3, 4 and 5. Only 1 unpaired electron, right? Now the thing is, 1 chlorine with its 1 unpaired electron will be overlapping from here. Another chlorine, it's plus minus sign. See, are you able to see the sign of the wave function? It is same. So chlorine, here it is 3p. Here also it's 3p is there for the formation of sigma bond. For the formation of sigma bond here. Right? Are we clear about it? Okay, so the thing is, I'll wind it up here for today, because I've got my next lecture also. And because of some technical issue, there was some problem here, not an issue. But the thing is, in the next class, I'll make it up for you. Don't worry about it. So we'll see the next portion in the next class. Are we fine on that? Are we fine on that? Okay, fine. So thank you and have a nice day, Vita. Thank you.